Oh yeah, and it's 2.5.
No, you know what? I was wrong. I did make it. It actually is 2.6. I lied to them. Whatever, we'll let them be confused. I gotta say, that first period class really is my guinea pig. Everything's so much more polished by the time I get here, which the sad thing is, yes, this is the polished version. But well, yeah.
Well, yes, we did get a better idea.
Okay, so today we're going to start talking about reactions. And now this is a huge branch in chemistry. It's an interesting branch in chemistry. Remember, when we start talking about organics, I mentioned this last class, but think of it this way. If you have a headache, what do you do? I come from an Italian family where my grandfather used to suggest that you just eat a clove of garlic.
That sounds fantastic.
No, I can assure you it's not. Now you're sick and you smell. And you already feel like you smell when you're sick. You know that feeling where you just feel like you're gross and you don't want people near you. Adding garlic to the mix is somehow not helpful. But that's what we did. But probably, in all likelihood, what you do if the headache is bad enough is you take an aspirin. You take a painkiller of some sort, right? You ever pause to think how weird it is that you can feel something in your brain, put something in your stomach, and your brain stops hurting? You ever stop to think about that? This is the type of thing I think about. We're like, that's weird. That would be like going, man, I'm really having trouble with the fuel injection system in my car. And someone goes, yeah, no, nothing to it. We're just gonna, tack this onto the gas tank and you'll be fine. It's weird, right? Yes. Yeah. No, but think about it. Like, it's amazing. And then what is it? It's just a little chemical. It's just a little compound. And yet you eat it, it goes into your stomach, it gets digested, ends up in your bloodstream. Unlike many other things, it's able to cross the blood-brain barrier because there's a barrier between most of your body and the brain that filters just about everything out of the blood, which we can agree is probably a good thing. And it's able to interact with the nerves in your brain and change their activity such that you no longer feel the pain you felt before. And we have a bunch of different ones of these chemicals that work by different methods by doing different things. And somebody has to make them, right? Somebody has to, A, discover this thing, figure out that it works, and then make it. And those people who sit in the lab and go, oh, hey, this person has, such and such a disease. Let's figure out a chemical that we can have them eat and it'll go through their body and fix that. Pretty mind-numbing stuff. I mean, it's astonishing. Like, I always just think, have you ever watched Jane Goodall? Does everyone know who Jane Goodall is? Yeah, she works with apes, and she's a lovely lady, but she'll go on these things and she'll be like, people talk about how important humans are, but apes are really smart. They can count to 10 and do simple arithmetic. And it's like, we build chemicals that you can put in your stomach and they fix your brain. It's an amazing thing. It's really impressive. And the idea that 250 years ago, we didn't know anything about any of this. Right? 300 years ago, we thought things were made of fire, earth, water, and air. And in that span, we've gone from that to the point where we can now design drugs to have specific effects on you by going into your body and reacting chemically with things. And to be clear, there's a lot of blind luck in this too. And there really is a lot of blind luck. A big part of pharmaceutical research is knowing that an animal will eat a certain plant in the wilderness and seems to have immunity from this thing, and so we go look at what the chemical is in there. It's not the case that we're sitting down and designing every drug from scratch. But still, we are designing them and we're figuring out how to make them and synthesize them. It's amazing stuff. And that's what we're talking about today. Now, we're going to start the simple side, but your first lab when we get back after the break is you're going to make aspirin. You're actually going to do a synthetic preparation of that right here in the lab, which is a pretty cool thing. Well, also, let's be very clear. Do not eat the aspirin you make. Like the first time somebody tries something, I just think like the first time I made pizza, it was pretty bad, but but the preparation of the pizza hadn't involved sodium hydroxide and hydrochloric acid, so I felt reasonably confident that it wouldn't kill me if I ate it. But like it still wasn't good, right? Does that make sense? Okay. Anyway, that's anyway. So today we're going to talk about on the note those three types of reactions. Today we're actually just going to talk about two, but there's one thing I just want to mention to end, which is that these reactions aren't hard. As we go through, you're going to see actually they make sense. They really do make sense. What is happening is not random. It's not out of the blue. They're very logical. They make visual spatial sense. We can picture them in 3D and really think about how they work, but they're specific. And that is a trend in organic chemistry. When you put two chemicals together, a lot of different things could potentially happen. So we're going to talk about a specific reaction that will happen, but the conditions have to be right. You know, I think back, like my wife and I, we went on a first date. If that first date I had thought, Harvey's sounds good, probably wouldn't be married with 2 kids right now. Maybe I would, probably wouldn't. Right? The conditions had to be right. You have to set. Harvey's is clearly the best of the fast food options, but it demonstrates good taste, really. Moving on. If I'd taken her to Arby's, she'd be with someone else right now.
Oh, Arby's is good too.
Okay, in all honesty, I would love to go to Arby's on the first date.
Well, there you go. Make it happen. Listen, the most important thing in a relationship is shared values. That's all I'm saying. And if you love delicious prime rib at an affordable price with whatever that cheese-based product is they put on top of it, the liquid cheese, then it's delicious. What do you get then? The curly fries are very good.
You don't get the beef and cheese. What is wrong with you?
Okay,
Are we talking about like a little burger, but on burger? Okay.
Yeah, they're good.
Well, you said something to do with ribs.
No, it's like roast beef basically.
Yeah.
It's like a cut of beef, but it's
I just get like the roast beef.
it's just cut really fine. It's good.
It basically looks like cold cuts.
My sister managed an Arby's all through high school. She started as just like the drive-thru thing, but she was a manager, and so I was always impressed actually when I went there. They had like a spotless kitchen. But the beef as it comes in is this like massive thing of just like, but it's not like it, like I worked at a restaurant where like beef came in and it was massive, but it was like a side and it had like the ribs on.
Yeah.
This was just like a tube of beef and it was big. Anyway, but it was like one of the cleanest kitchens I've ever seen in my life. So I was impressed by that. Anyway, I feel as though I'm losing the point here. Yeah. Okay. Focus. Don't be interested in me. I'm the center of attention here. Okay, so no, Arby's is not French dining. Moving on. No, seriously, let me focus. There'll be time. But
I think we should just clip this little part out of the live stream and put it on in our graduation video.
I like that.
All the clips of every single one of your videos, just that's off topic.
It would be
doing chemistry.
It would be so much longer than a video of my lessons.
I think it's better than the actual graduation.
Anyway.
Get my diploma. Let's watch these.
Anyway, like preparing affordable but delicious food, organic chemistry requires specificity. And here's what I mean. If you took that side of beef and you put it in the oven and the instructions said you had to cook it at 250, if you put it in at 350, what would happen? It would cook faster, and then you would have a charred outside and a raw inside, right? In other words, you would get a different product than what you were looking for. What if we put it in at 115? You would get salmonella poisoning. That's what would happen. You would get sick. So don't do that. You would get a different reaction than you intended. So the conditions matter. Likewise, in organic chemistry, the conditions of the reaction matter. So in every one of these reactions, we're going to talk about what reacts, what the outcome is, but we're also going to often talk about the conditions that have to be there, and that matters. It will definitely be something you're expected to know and to understand why. So let's look at the first example. The first thing is substitution reactions. Now, to have a substitute teacher in class, two things have to happen. What are they? The main teacher has to, let's say, be at a family event. You know, I don't want to die. So I've got my court date, you know, for whatever. So I'm at court for having finally lost it on Kyle and just couldn't handle it. So I have to be gone, and what else has to happen?
Somebody has to come in.
Parks has to-
Good. Parks has to come in. That's exactly what happens here. In the first case, we're talking about reactions where we take an organic compound, we are going to remove something, and we're going to replace it with something else. These are called substitution reactions. And for the purpose of this course, we're going to assume that those only happen with alkanes, just simple straight chains. Now they can potentially have functional groups on them, we'll get to that, but essentially we're talking about simple straight chains. So I want to look at the first example, and we're going to pick a nice, easy alkane. In this case, ethane. Did I draw that right?
Yep.
And we're going to react it with, when an alkane and a halogen. What's a halogen? Okay, so what are they? Sure, pick one. Bromine it is. So like this? Why no? Good. Like this. Okay. So we're going to react ethane with bromine. It's a substitution reaction, which means on the main chain, something has to leave. What's going to leave? A hydrogen. Does it matter which one? Not in this case. It has to be on a terminal carbon, as a rule of thumb. As a rule of thumb, it's going to happen on the terminal carbon. And remember that these can rotate freely, so no one is preferred to the others, right? The angles are all the same, they rotate freely. I'm going to pick this one. And what's going to take its place? Bromine. Both of the bromines? Why just the one? But why couldn't they both attach? Good. How many bonds can bromine make? Just one. So only one of the bromines can attach. So what will my product be? Well, what's it called? Okay, sure. But the main thing. So I have this, and then what's connected where the hydrogen used to be? Bromine. What do we call this guy? Bromo, ethane. And in this case, I don't need a number because it's always going to be carbon 1, right? And then, yeah, McGowan, you jumped ahead of me there, which is fine. What else do I have? That's right. The hydrogen that left has to go somewhere, and it's going to form a bond with the bromine that was left behind. Now again, does that reaction make sense just on a fundamental level? It seems to make sense to me, right? If we want to replace a hydrogen, we can put something near it, let it bump into it. That's exactly what happens. They bump into each other. And the bromine, being electronegative, is going to want to get electrons. And keep in mind, the bromines bound to each other have an equal pull on electrons. So neither one really loves that arrangement because they have to share them equally. So as the bromine gets close to that hydrogen, it finds something that it can have a really unequal sharing with, right? So it's going to pull that hydrogen in instead of remaining bound to the other bromine. And that's the way this reaction happens, is it's energetically favorable for the bromine to steal that hydrogen off the main chain. But now the main chain is looking to make another bond. And what is available? A bromine. So they bond. And that's the reaction mechanism, yeah.
Would you get a situation where both bromines attach like to where individual parts would be
It's a good question. The answer is no, actually. Substitution reactions happen one at a time. Now, could I put a second bromine on here? Yeah, I could bring another diatomic bromine up to it. But this reaction is done. So they happen one at a time. Just like we don't substitute two teachers out at a time, right? Just one at a time. We take one out, we replace with another. Then if another one goes, but it's weird to think of a situation where, you know what I mean? That's a crappy analogy, but it's the best I had in my head. But they happen one at a time. Do I want to give you the general form? I think this is fine. And again, it happens on the terminal carbon most often. It can happen to an interior carbon, but if you think the terminal carbons have more hydrogens there, they're statistically more likely to be the ones that are reacted with. This is the most common outcome. We will always, in this course, we'll assume that it will. Now, for a reaction to happen, we need some input of energy. But remember, just like the baking analogy, too much energy, I might get a totally different reaction. Not enough energy, I won't get a reaction. So this is another one of these cases where we talk about the specificity. This one works well with just the energy provided by a bit of, it's in the description, light. If I put these together and lock them in a cabinet, I won't get a reaction. If I put them together and leave them under lights, it will happen. So we need to provide light to make this reaction happen. And again, it's not that light has some mystical, magical property. It's enough energy, but not too much energy. Does that make sense? It's like the oven set to 350. There's nothing magical about the number 350. It's just that food tends to cook nicely there, you know, but some foods you need less energy, some you need more. This is a case where the amount of energy we need is just some light. That's one example of a substitution, all right? Replacing a hydrogen with a halogen. And we get something called a haloalkane, right? Which is something we've already known about. This is called a halogenation reaction, by the way. Not a very creative name. That's right. And again, substitution, because the halogen does get attached, but it has to remove something to do so. Now, this example, too, is also a substitution reaction, but to show that there can be functional groups involved. So here, we're going to react, we're going to make a haloalkane again. So again, we're going to make a chain of carbon with a halogen on it, but this time we're going to do it using an alcohol to start off. Now, you can do this with any alcohol, but some alcohols make it easier than others. If we tested with ethanol, say, it would work, but we actually have to put quite a lot of energy in. We really have to heat the thing up. Ethanol is primary, secondary, tertiary alcohol. Good. And we found if we took a secondary alcohol, say propan-2-ol, that it would require less energy. We'd still have to heat it, but not as much. And then we found if you use a tertiary alcohol, right? What's a tertiary alcohol? Good. That would actually happen at room temperature. So the more bonds the carbon is making that's attached to, the easier it is to remove that alcohol. They often will. They often will. So we're going to look at one of those examples, but I want to keep in mind that this can happen for any type of alcohol, but the type of alcohol determines, again, those very specific conditions we need to meet. So here we're going to use a tertiary alcohol, and we're going to use one that looks like this. The red tells you it's important. Like in some Bibles, they put everything Jesus said in red letters. Never really understood that. But but they do. That's a thing. Anyway, so this is like, I'm not trying to compare a hydroxyl group to Jesus, by the way. It occurs to me that that was an insensitive comment that I really didn't mean in any sort of insensitive way, but I just moved it. I just want more space because I have a habit of going over the page here and that's annoying me. So I'm just moving it. Oh yeah, if you hold the second button, you can group things. Just slide it over. Anyway, so we're going to react this in this case with a hydrogen halide. What's a hydrogen halide? We just made one actually, didn't we? Here we made hydrogen. Yeah, so we made hydrogen bromide before. Have you seen him? You could move it to like room 37. You'd be fine. No, it's room 31, though it's that way. But I picked a number. Yeah. Okay. Anyway, so here we're going to use HCl. Don't tell me what to do. Do you want hydrogen iodide? Okay. 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 I don't know why I'm so resistant to iodine. Just keep yours how it is. It doesn't matter. Okay. Anyway. Now, this substitution reaction can happen right at room temperature. Doesn't need any special conditions. Nope. Nope, this one will happen. The amount of energy just in ambient temperature is enough for this to happen. Light won't make it work or not. It's fine. The reaction, of course, is going to happen between these. And so with what will I end up? First of all, let's name this one. What would this be called, this alcohol? Two methyl propan 2-ol, and it's reacting with what's this thing? Hydrogen iodide. All right, so what's going to get removed? Because it's a substitution reaction, so something has to get taken away. What gets taken away? Good, so the alcohol is going to leave. What's going to take its place? The iodine. Good. Keep in mind, what drives this reaction is that oxygen on the alcohol is going to want to have a more favorable bond for itself. So it's not going to want the iodine. It's going to want the hydrogen so it can have a more favorable dipole. Does that make sense? So, yeah, it's this tendency, right, to... They want this. Of course, they don't want anything. They're bound by an entropic need to minimize the amount of energy it takes to do things. But really, people aren't much different, are they? We just think about it first, but we're equally lazy. All right, and what am I going to have left over? Good. I'm going to have the hydroxide, and it's going to be bound to the hydrogen from here. And there we go. And so we end up with, what would this be called? Still a 2-methyl prop, but now it's a 2-methyl. Oh, is that in the right alphabetical order? No. 2-iodo, 2-methyl propane. Good. It's no longer an alcohol. And so if you wanted to play like a hilarious party prank, you could take ethanol and add, a hydrogen halide and de-alcoholize all the booze. Though you'd be filling it with, no, you wouldn't. You'd be filling it with, I don't know anything about haloalkanes, like what the outcome of that would be. I don't imagine they're good for you, but I don't know. But one way to find out, my friend Chris tells the story of his brother, and it's probably not a true story, but I desperately want it to be a true story. So I just tell it like it is. But he swears up and down, he swears on his mother's life, that when his brother Tom was in university, they held a kegger with non-alcoholic beer. and watched people just behave ridiculously as if they were really drunk, knowing full well that everyone was actually completely sober because there was no alcohol involved. And again, I don't know if that's a true story or not, but I want it to be a true story.
Possible, yeah.
But I know as a bartender, when somebody had begun to have too much to drink, that sometimes if you tried to fight with them, they'd get and be like, no, I won't give you another drink. They'd get very aggressive. Whereas if you just gave them a glass of water and told them it was something, they would just drink away, and you'd just slowly be hydrating them before you sent them off in a cab. So I could believe it. Anyway.
It's very possible.
Well, yeah, and people, yeah.
Take a sugar pill and change the entire.
This is the same guy. Have I told you about Dodi Bresner? This is the same guy who invented a fake person. And this one I know is true because I've met one of the victims of this for the same university he went to. He's not a very nice person, as it turns out, Tom. Maybe I'll show him this video one day. But he's got a big sense of humor. So they had gone to a small school in Calgary, and I can't remember what school was. But so it was a pretty small cohort of people. And so they were always hanging out together and going to dinner together, this or that. So Tom and 3 of his other friends started talking all the time about this person, Dodi Bresner, who was not a real person. This was just somebody they had made up. And but they would just talk about all the time. People would go, I don't think I've met Dodi. Like, oh, you totally have. Remember like last Tuesday when we were at Swiss Chalet? He was right at the end of the table. He was the one telling the stories about like his time working in the Foreign Service, and and this went on for months. And and nobody called them on it. And you have to think that at some point somebody would. And then slowly, like other people would start to mention Dodi casually. But of course, this person isn't real. And then apparently one day in the middle of a class, like at a lecture or something, they were at some kind of event where you were supposed to be kind of studiously doing something, somebody went, Dodi Bresner isn't real. Anyway, so the human mind is an interesting thing. Also, that's a ridiculous name. But anyway.
It's usually those ridiculous names so that it would be unsuspecting.
Yeah, because who would make that? And by the way, if you have like an Uncle Dodi, I apologize, but it's not a name I'm familiar with. Anyway. There you go. See, with a nickname like that, he should be real. Okay, so we've talked about substitution reactions. Now, a substitution reaction is a case where we remove the teacher and we replace it with a new one, right? We remove a hydrogen, we replace it with something. We remove an alcohol, we replace it with something. But we have to physically remove atoms from the hydrocarbon to put new things on. What if we wanted to add new things without taking anything away? What if we wanted to do a true addition? What if the admin decided, Orlando's really not getting the job done, and they decided to put a second teacher in here with me, but they didn't remove me, in some sense of pity, or because I assume they get some sort of extra funding from the government for keeping me around as some sort of like make work project. For people with like severe brain damage, which I was obviously dropped or something early on in the process. That's right, you guys are all guinea pigs in some awful experiment. But if they finally decided to put another teacher in the room, could we think of a case where we could add new atoms to a hydrocarbon chain without having to take any atoms away? What would we need? Put your hand down. Yeah. A double or triple bond. Because if we break that double bond, that carbon is now ready. Each of those 2 carbons that was making the double bond is ready to make a new bond. And we didn't have to take any atoms away. Does that make sense? A double bond is a second bond between 2 carbons. So if we break it, those carbons are still stuck together. We haven't taken anything away, but we now have a bond on each of those carbons to work with. And these types of reactions are called addition reactions because we're adding something in, but we're not taking anything away. This is a net increase in the number of atoms. So these are addition reactions, and they're when new atoms are added to a molecule without the removal of old ones. This can only occur if a double bond is present in the primary chain, alkenes. I suppose it could happen with alkynes, and yet I don't know, so I'm just not going to talk about that because I haven't thought about it and I haven't looked it up. So I want to look at a simple example, ethene. What's ethene look like? Yeah, so we got 2 carbons. They've got a double bond between them. And of course, they have 2 hydrogens. Of course, the hybridization state of these carbons is sp2, so these bond angles would be good, very good. So there we go. And we're going to react this with bromine. I don't know why I said gas. I guess it's in a slightly warm situation because bromine at room temperature is a liquid. Anyway, yeah. It's a very fine balance. It boils at a very low temperature, but it's actually liquid at room temperature. Anyway, don't worry about it. Okay, so here we go. Now, remember that reactions are violent things. A collision has to take place. Where are these going to collide? Where does the bromine have to attack? And that is the language we use, by the way. The attack happens. Isn't that aggressive language? It's like war. Yeah, the attack has to happen at the double bond. And in this case, it breaks the double bond. And when it breaks the double bond, we end up with something that looks like this. Carbon with a single bond to another carbon, and they have 2 hydrogens. And both of these are obviously ready to make 2 new bonds, right? Does that make sense? And what are they going to bond to?
Bromine.
Yeah, because it's the only thing available, right? So let's name all these things. This is called ethene. We know that. What is this called? Yeah, just bromine. Okay, you jumped ahead, but I'm going to let you do it. Okay, what's this called? 1,2. Specifically, how many bromos? Good. 1,2-dibromo ethane. Good. My violin teacher, when I get a note wrong, she has this incredibly annoying thing she does where she goes, "Are you sure it's a G sharp?" And I go, "Obviously, since you're asking, I'm not sure it's a G sharp." But that's it. But every time it's like, "Are you sure?" No, I'm not sure. Yeah, I'm bad. It's pretty sad. No. Like, here's the deal. I'm no great guitar player, but I can like make it make sounds that sound like a guitar. When I play the violin, like the SPCA gets called, and they're like, somebody's abusing animals in this house. Like it's bad. I don't sleep, but violin. Like if I practice and my children like are on the same floor as me, they'll be like, "Dad, stop! It's awful!" And they'll be like, "How am I supposed to get better if I don't practice, kids?" And yeah, anyway, it's bad. But anyway, yeah. So, but always.
The dogs from downstairs.
Yeah, oh yeah. Are you sure it's an F sharp? So in this case, are you sure it's bromo? Dibromo. Good. Okay. So an addition reaction happens by breaking a double bond, and then each of the constituents of this thing it's reacting with end up making a bond. Shh. Let's look at a second example. I want to make propene. So what is the structure of propene? Prop means it is 3 carbons. Yeah, and of course we don't need to give it a number because either way we count it would end up being a double bond on the first carbon, right? So 2 hydrogens here. How many hydrogens off this one? 3? 1, good. Okay, what about this one?
3.
Good. Okay, and what am I reacting this with? Water. That's boring.
No. He's trying to, but he doesn't have to.
Was. Okay, so. Oh, sorry, did that come out? Okay, so where is this attack going to happen?
Double bond.
At the double bond. Good. Okay. Okay, so the double bond is going to attack. So I want to just draw what we'll be left with before showing the additions. So we're going to have C. It'll still have its 2 hydrogens. and then this C will still have its one hydrogen, then this. But both of those first two carbons are now ready to make another bond, right? Now, what do I have to add? I have a hydrogen and I have an OH. I have a hydroxide. Does that make sense? The water is going to split up into two parts. One of those parts will just be a hydrogen. One of those parts will be an OH. Now, at this point, you should be saying, it is going to make an alcohol, but it could make two different alcohols, couldn't it? It could make propan 1-ol, or it could make propan 2-ol. How do we know which? The short answer is that it can and will make both, but one of them is energetically favorable. And this comes back to the point where we talked about this course being a lot about kind of nitty-gritty specific details. Both of these are possible outcomes, but one actually happens in quantity in nature, and the other doesn't. We would really have to design a different synthetic process to get the other one, because it's not favorable using this kind of reaction. And that's why some things are tricky to make. One of these is easy to make because it wants to happen. So we are anthropomorphizing it again, right? It wants to do it, but it naturally has a tendency to do it. The other is not energetically favorable, so it doesn't. So the question is, how do we know? Well, but it's closer to what? It's closer to the H or it's closer to the OH. So there's a rule. And the rule is discovered, by the way, did this guy like sit down and think this through and figure it out? No. He experimented, he tested it. So this fellow Markovnikov has a rule. And what Markovnikov discovered is that in general, when we do an addition reaction, we break a double bond. And often there's a case where the hydrogen that is moving on can go in two places, just like here. It'll either have a hydrogen on carbon 1 or a hydrogen on carbon 2. And Markovnikov discovered that in general, the hydrogen will go where there are lots of hydrogens already. This makes sense. When I was in grade 7 and going to school dances, you would walk into the dance, and there would be one side of the room that had lots of girls, and one side of the room that had lots of boys. Which side do you suppose we all went to? Your own side, because you felt safe there and unafraid and comfortable, right? If you have a choice to go to a party this weekend and one has a lot of your friends at it and the other doesn't, presumably you will probably go to the one. That's your friends.
I'll be doing chemistry.
If there were two groups of people studying this weekend, and one of them was made up of smart people, and yeah, no. The point being, as a rule, as a way to remember this, we imagine that people typically go where they feel comfortable, right? And we find that hard. Or another way to think of it is that the rich get richer. You know, I read an interesting article that, you know, we talk about Donald Trump as this investing genius, but Donald Trump inherited about $20 million. And somebody made the point that if in 1982, when he inherited $20 million, if he had taken that and blindly invested it in an indexed stock portfolio, just a stock portfolio that said just follow the S&P 500, which is just this basic, bland, no frills. That's one of the ways we measure how the stock market in general is moving up. If he had taken his $20 million and invested it there, he'd be worth $7 billion today. Estimates show that he's worth somewhere between $3 and $10 billion today, depending on who you ask. If you ask him, he says 10. If you ask economists, they say 3. If you ask him, part of his thing is he's valued his brand name, i.e. his own name, at $5 billion, which, by the way, is probably not an unreasonable assumption, because most of how he makes his money, people think he builds hotels. He doesn't. Hotels build themselves and then license his name. After they've already been built, they give him a paycheck to say, can we put your name on the side of it? And this is how this guy makes money. But it shows us a fundamental principle. The rich get richer. You know, it's we hear this all the time, right? Like there's been a big uproar lately where people go, and the politics of it I don't care about. Or I do care about, but I'm not discussing my political opinion in this class. But people say, oh, Kathleen Wynne wants to give free tuition to everybody. That's ridiculous, And I had a friend who put a big long rant on Facebook where she said, I came from a family with not a lot of money, and I, saved and scrimped and worked full time. Mind you, tuition was $4,000 a year when we were going to university, not 15. But I scrimped and saved and paid my way through. It used to be you could pay for a year of university easily with 4 good weeks of work, and that is not the case now, right? So you have to think about that. You could pay for a whole semester with 4 weeks of work, 8 weeks of work, your whole year. So it's a different time, but that's neither here nor there. But that misses the entire point, which is that it is still the case today that the number one predictor of whether or not you'll go to university is not if you're smart, not if you did well in school, not if you had good grades, not if you have an IQ that's high, not if you write tests well, it's how much money your family has. The number one greatest predictor of where you're going. All right? We know that to be true in real life, and Markovnikov showed us it's true in chemical life, that the hydrogen will tend to go where the other hydrogens are. That was good, right? That's smooth. When I went to Brock University, I used to write for the Brock Press. I wrote the political column, but for a period of about 2 months, it was called like the right hook and the left jab. And so somebody would write like a liberal position, and then I got hired writing the conservative position. And then the guy who was writing the liberal position quit. So for about 3 weeks, I wrote both. Then I quit. But it was a really fun time in my life where every week I would write 2 articles on the same topic disagreeing with themselves, one under my name because I'd already been writing, and then the other one under a fake name. And my claim, and this has a bit of language in it, I'm sorry, but I had written an article one week, and one of them was about how they should give free tuition, and then the other one that I wrote under my own name was that they should actually raise tuition, but make it free for people under a certain income bracket, like the University of California does, where if your family makes less than $75,000 a year, you shouldn't pay a dime. But at the time, I said that if your family made more than $100,000, you should have to pay the whole span. So anyway, but the title of my article on the other side was "Raise Tuition Now." And I was walking down the hall at Brock one day, and I heard somebody with a newspaper go, "Joe Orlando, what an asshole." I thought, that's me. Anyway.
Was the fake name Dirty Person?
No. That's a good question. I don't even know what it was. No, you know what? I think they just kept the name of the guy who had been writing it on there, which is that poor guy, because he was like a good writer, and I'm garbage. My writing was terrible.
You should write a book.
No, I really shouldn't.
Stories.
No, it's not as exciting as it sounds. Chemistry is just boring enough that my stories seem more interesting than they are. So, all of which is to say, hydrogen, this hydrogen, the red one right over here, when it gets added to this compound, is going to want to generally go to the carbon that has more hydrogens to begin with. So on the side over here, is it going to go here or here? Carbon 1 or carbon 2? Carbon 1. And what will go on carbon 2? The OH. And what we end up with is, what is the name of this alcohol? Propan 2-all. Good. And that follows Markovnikov's rule. So if we look at both these examples, addition reactions simply involve breaking a double bond and then allowing the compounds next to it to fill those empty bonds. I want you to try the third example. 2-methylbutetuene reacts with hydrogen bromide. And make sure you follow Markovnikov's rule when you do so. Oh, it is. Are you kidding? Mashinsky's rule would be a great rule. I'm going to plug this in and it's going to die and then I'm going to be angry.
Is the 5 a part of the?
What?
Example 5.
Example 5.
No, it's example 5.
Really, I was always confused, but I didn't think that francium, even though it says on that table, was liquid at room temperature. And it technically isn't. Its melting point is 27 degrees, and I think 23, right?
Yeah.
So.
Yeah. You want to mix salad real quick?
I was scared of it because I thought it is, but it turns out it's refreshing.
That's so funny.
I was like,
But in this case, just one of them is good. This is
you
a
just imagine that you like going over the grade, just be on the ground and be like, oh, I think words. God, yeah.
Can't press it? You can't. Okay, is that cool? So, here, I just. Would you rather here's the library?
I don't know. Library's okay.
Okay, let's do library.
No, I will. It
Sounds
actually will.
Yeah, that's true.
You That's how you farm worms, dude. You just rip them in half when they get old enough.
Have you seen that movie? I don't know. Okay.
It's not the And I said that you can farm worms by ripping them in half.
That's true, yeah. Okay, let's focus. Okay, I'm gonna let you carry on. But quickly, 2-methyl-but-2-ene, what's that look like? Oh, okay, fair enough. Could you tell me how to draw it? For a carbon chain? First and second? Second and third. And? Good, and then obviously we just fill the gaps in with hydrogens, right?
Don't do that.
Don't tell me what to do.
That is wrong.
Oh, is it? Okay, what's it reacting with? Good. H. Oh. Okay, so there we go. And when we react these, obviously the first thing that happens is what is the first thing that happens? Double bond breaks. Good. So I'm still going to have the carbon here, carbon here, carbon here, carbon here. This will still have H's. This will still have just one H. This will have a methyl group. And this will have all its H's. What has to fill these two obvious spots where bonds can happen? The hydrogen and the bromine. What's going to go where? Okay, and on carbon 2, bromine. Why? Good. So the Markovnikov rule tells us that carbon 3 is going to get the extra hydrogen because it has one to begin with. What's the name of this final guy? What is it? I'm so sorry. 2-bromo, 2-methyl, butane. Good. And again, if we wanted to make 3-bromo, 2-methyl butane, it would actually be a tough thing to do. This is easy to synthesize because this is the reaction that naturally wants to happen. And it's interesting because you can imagine when a scientist sits down and knows what he wants to make, if it follows if what he wants to make happens to be Markovnikin, right? If it happens to be like this, then that's a nice, easy thing to synthesize, right? It's easy to do. If, on the other hand, for whatever reason, he wants to synthesize something that breaks that rule, then he has to do a complex series of reactions to get there. That's what makes organic chemistry so interesting and so challenging. In the 4 minutes that remain, would you mind putting in those? Thank you so much. Your interim reports are coming around. Make sure they agree with what you have in your own records in terms of marks. If there's any disagreement, let me know. There's some assignments and some tests up here and some quizzes. Please come get them. They're crowding me out up here on my control. I should have everything from Unit 1 marked now. If there's something from Unit 1 not marked in there, let me know. Your lab books have all been marked. They're not here, but they're marked. I can't remember if I included them in this report or not. I think I'd answered some of them and not others. Yeah. You should get it.
Yeah, my lab's done.
That's okay. It's a small mark at this point because it was a pretty basic lab, but they are marked. So I'll get those back to you when we get back. Again, really quickly, I am going to put a brief little assignment up over the March break. I'm not a guy who's trying to make you do work over the March break. In fact, specifically, if you're not planning on studying a lot over the March break, I'd encourage you not to do it during the March break. I'd encourage you to do it the day before, because here's what I'd like. Listen, I want everyone to have a nice break. Study as much or as little as you think you need to. Spend as much time or as little time on school as you think you need to. But the day before, 2 days before we come back, I want you to look at this assignment. That'll be online and do it, because I want to make sure that everyone's coming back reasonably fresh with the material. Is that fair? I don't want people coming back not having looked at this since today. So I am going to put a little assignment up over the March break. It's not a big thing, but it's just a little refresher to make sure that we're picking up at this point and not picking up with people who haven't looked at anything this week.
So it's due when we get back.
That's right. Okay? Any questions? I'm trying to figure out. What activity on 17? That was, it was, you were in this class, but they signed you at the end of the day, so your mark absent the whole day. It was when you went to, Sunday. Oh. Don't worry, it's not affecting. No, I know. It's just the way Trillium, look at you knowing about, does everyone know about